Okay, a new coordinate system. We're going to call it a polar coordinate system. Some of you have probably seen this before. Some of you might not have seen this before. So let's just go over it from scratch and make sure that we're all clear on the meaning of all this. We have our regular rectangular coordinate system, also known as Cartesian coordinate system, Euclidean two-space. And what does it mean? Well, we specify a given point, or a given point is determined by an x and y coordinate. And we're pretty familiar with that. The new, so here's x comma y. The new approach, or a different approach rather, is to say, let's specify that distance. Let's call it r. And we will also specify this angle. Let's call it theta. So if somebody tells me theta, this angle, and they tell me the distance from the origin to the point, that uniquely determines a point in the plane. Now, what we want to be able to do is to flip-flop back and forth. You give me xy, I can tell what r theta is. You tell me r theta, I can tell you what xy is. So let's go ahead and get that out of the way. And it's kind of nice because it's pretty straightforward. There's no trickery or ingeniously clever steps that have to be performed here. We can just look at a good old right triangle right here, call this x and y. Well, this x is this x and this y is this y. So look at this picture right here. We have cosine of theta is equal to x over r, of course. And sine of theta is equal to y over r. And let's go ahead and solve both those for x. So we get x is equal to r cosine theta, and y is equal to r sine theta. I'll put those in a box right now. Whenever dealing with polar coordinates, you either want to have this floating around in your thoughts or have it written down on a piece of paper, preferably at hand, right in front of you. Now, I'll go ahead and erase this. We want to be able to go the other way around. In other words, if someone were to tell us x and y, we could tell what r and theta are. And I suppose there's many ways to go about doing this. Again, we imagine that we are given x and y, and we want to get r and theta. Well, just take a look at this picture right here. If somebody gave me, I'm tempted to do this a different way. I don't know if I should do it that way or not. Look, you can look at this as two equations and two unknowns, and you can solve for r and theta. That might be an interesting exercise. At the same time, I guess I could just look at this picture here and apply the Pythagorean theorem. And what would the Pythagorean theorem say? It would say x squared plus y squared equals r squared. Now remember, here's a case where I'm assuming I know x and y, and I want to determine r and theta. So we square root both sides, and what that means is we get r is equal to this rather familiar looking form. Now, what about theta? There's a couple of different things that are occurring to me right now. One, like I said, is to solve this as the two equations and two unknowns. Use substitution and solve for r and theta. You would get that for r. What was the other thing that just popped into my head? Oh, a kind of a slick way maybe of looking at this just popped into my head. If I take this equation and I divide by this equation, what do we get? Well, look, if I take this and I divide by this, the r's will cancel out. I'll have sine over cosine, which is tangent. And then what would I have on the other side? I'd have y over x. Well, this should actually come as no shock because look at the picture. What's tangent of theta? Opposite over adjacent. And what does it mean for theta? Tan inverse of y over x. So what is theta? It's tan inverse of y over x. Quick comment, something you may or may not have seen before. What's y over x? Another way to look at that is the slope. So you've probably seen this before, but nonetheless, tangent of the angle subtended by the line and the x-axis is equal to the slope. and the angle made thus is a tangent inverse of the slope. Okay, but at any rate, you see these four right here. You want to make sure you have these at hand whenever dealing with polar coordinates. And there's a bunch of problems in the book, and they're good, and I think you should go through them, and you can ask me if you have any questions on them. Plotting points, basically switching back and forth from rectangular coordinates to polar coordinates. But here's what we want to do. We want to go one step further. Now, the book doesn't do this yet, but it's going to have to do it sooner or later. And I'm thinking, let's just go ahead and do it now. And let's move this up to 3 dimensions. 3 dimensions. Now, there's different ways, I suppose, one could propose that we go about doing this. There's the x-axis, the y-axis, and the z-axis. Now, you have to imagine a point in space. So how would I normally think to specify this point? I would give you the x-coordinate, the y-coordinate, and the z-coordinate. So we come out some distance on the x-axis, out here. Let's say that's x. And then we go out in the y direction some distance. And then maybe we go up in the z direction. So we get this point right here, x comma y comma z. And I can think of that as a vector, right? In fact, let me draw this in like this. I'm not sure the arrow at the end of the vector wouldn't make matters any better here, so I'll just leave it off for right now. Now, as far as drawing this in here, here's where your drawing abilities start to come into play. I said come out over here, x, and then go over some distance, y, and then up a distance, z. Maybe I should hear this is the x-axis, go way out like that so we don't get mixed up here. Now, how do we write this in terms of polar coordinates? Now, what's the idea of polar coordinates? Well, one of the ideas is definitely we want to have the distance from the origin, usually referred to as the pole, to the point in question. So we'll call this distance r. Now, different books will call it different things, but I'll just call it r. It sounds like radius, and if you do a circle around the origin, you can maybe see why that's a useful sort of letter. Now, what else would I need to specify this this point? Here, let's see if I can get this drawn in here. Here we go. This is x, this distance here, and it's also over here like this. I would like you to think of the rectangle in the xy plane. The rectangle is the one that comes out x amount parallel to the x-axis, and then over this direction an amount of y parallel to the y-axis. So think of this rectangle. And now let me get a different colored marker here. Might be a really good time for that. Consider that diagonal. Now that diagonal is in the xy plane. It's in the xy plane. And I want you to think of the following angle right here. That angle is the angle between the x-axis and this diagonal line, and all of that happens in the xy plane. And I'm going to call that theta. And if you remember what we just did with 2 dimensions, the xy coordinate system, that really is staying the same. In a sense, r is the same, although we're up out of the xy plane, but this angle right here stays the same. Now, here's where things get interesting. We need something else, because that wouldn't tell us where this point was right here. In fact, you could imagine if this was like a fixed physical stick right here, you could sort of rotate this up and down like this, and it would still have the same value of r and the same value of theta. So r and theta is not enough to tell us where we are. We do need something else. And what's interesting now is there's 2 ways you could proceed. I'm thinking right now for purposes that I have in mind, a problem I want to do. as soon as I finish doing this. Now, not all books will agree with this, okay? I want us to consider this angle right here. We gotta use a different color here. The angle between the vector r and the xy plane. So what is this angle right here? Well, what this angle is really is, if you thought of this diagonal line coming out like this, it's raised up like that. And I'm going to call this phi, this angle phi. I don't need that y right there anymore. It's not doing me any good. I'm going to call this angle phi like that. And what we get here is, instead of x, y, z specifying the point, we have r, theta, phi. Now, different books will actually put these in different orders and use different symbols. Can that be confusing? Yeah, it actually can. I quickly was curious about something, and I noticed, I don't know why, but on Wikipedia they make a point of this, and I think it's a good thing to make a point of, particularly because some books will switch these two, and some people will specify this angle, instead of from this plane to this vector, from the z-axis down to this vector, and those are just as it's. I mean, there's no real, I suppose, immediate reason why you'd want to do it one way or the other. For purposes I have in mind right now, I'm going to do it this way. We'll stick with this way, unless the book does it the other way when the book introduces this, and then I'll probably switch it around. Well, how do we go? We want to be like over here. We went from xy. Sorry, we went from r theta to xy, and from xy to r theta. We want to be able to do the same thing. Okay, so how are we going to do that? Well, let's see. Let's suppose we're given. We're given x, y, and z. So we know x, y, and z. Well, I don't think I need to reinvent the wheel. I have a tendency to do that all the time, but we just use the good old Pythagorean theorem generalized to 3D, and we get r. So r is the square root of x squared plus y squared plus z squared. It's just the length of this line segment, this vector. It's just magnitude. It goes by a lot of different names. Maybe you haven't seen that before. I should not deprive you of the opportunity of proving it. So I don't know, close your eyes for a second if you don't want to see this. This is a right angle right here. This is x by y. This triangle, or sorry, well, if you look at this diagonal right here, that's a triangle in the plane. There's x, y, it's a right angle. It may be a little hard to visualize, but this is the hypotenuse. And the hypotenuse here is the square root of x squared plus y squared. Now, again, this is actually somewhat difficult to visualize, but especially because I wrote that right there. Let me write it right here. Square root of x squared plus y squared. That's a right angle right there. That's coming up out of the xy plane. And this is z. So if I use the Pythagorean theorem on this triangle, the triangle which is, it's sitting perpendicular to the xy plane, the Pythagorean theorem applied to that would say this side squared, x squared plus y squared plus this side squared, z squared, equals the hypotenuse squared. And that's where we get that. So no mystery there, no secret, nothing particularly special. So this says, given x, y, and z, I can tell you what r is. Well, let's just continue on and get theta and phi. Hey, once we get these, we don't have to ever go back and do this again. So we had these formulas over here for 2D. Good, there they are. We don't ever want to repeat that. They're good as they are. We can look them up, we can remember them, but we don't need to hash that out again. Looking at this picture right there, there's the right angle. Where's the hypotenuse on this? Let's see here. The question is, do we want to use sine, cosine, or tangent? given this angle right here? Well, I guess I'm thinking tangent. So tangent of theta, what is tangent? It's opposite over adjacent. So it's y over x. So theta is, I'll write it up here. So theta is equal to tangent inverse of y divided by x. So again, if I'm given x, y, z, here's how we calculate r. Here's how we calculate theta. And then what about phi? Well, let's see. Where's phi in the picture? Phi is right here. Do we want to use sine, cosine, or tangent? Well, I guess I used tangent a minute ago, so let's continue on in that vein. Tangent phi. What's definition of tangent? Opposite over adjacent. So this is z over the square root of x squared plus y squared. And so phi is equal to tangent inverse of z divided by the square root of x squared plus y squared. These formulas here are more complicated than that, but I guess we'd expect that. It's in 3 dimensions. Now, what do we also want to be able to do? Well, one thing is I want to have these where I can refer, again, I only said this, but I want to have these where we can refer to these. We don't want to have to go through this business all over again. It can be somewhat dangerous looking this up, again, because different people use different symbols, different books, texts, individuals. So you do need to be cautious. The other thing is this. Let's go back to theta right here. When finding theta, I didn't have to use tangent. I could use sine. What's sine of theta? Y divided by this. And then we would have theta is equal to sine inverse of y divided by this. And I could have just as well done that. So you might see different versions of all these formulas here. And I think what I should really do is make sure that, say, for example, in class, let me think about this. But once we establish, say, this and this, let's just agree in this course to absolutely stick with that, unless we make a big fuss about doing something different. Now, what's the final thing we need to do to sort of finish this off? The final thing we need to do is say suppose we're given r, theta, and phi. What are x, y, and z? What are x, y, and z? Well, if we're given r, let's see, we're given r, and we're given phi, that means I can determine the length of this hypotenuse. And if nothing else, maybe I can't think of what else to do. It gives me something to do. And that's good. So it's funny, that kind of hypotenuse in that picture, that comes up every once in a while in problems. I'm always caught at a loss for what I want to label it. I'm just going to label it right now, lowercase d for diagonal. That may not be the most elegant solution, but that's what I'm going to call it. So looking at this picture right here, what should we use? The sine, cosine, or tangent? I guess cosine. So cosine of phi. What's cosine of phi? D over r. So looking at this right here, what does that give us for d? D is equal to r cosine of phi. And I have to keep track of what I was given. I was given this, so I know this, so that means we know d. Now that we know d, we know the hypotenuse of this right triangle, and I think pretty easily we can go after x and y. So let's do that. Remember, now we want to think, and at least in our minds, we know d. Look at this right triangle here, and what do we have? We know theta too, right? So what is cosine of theta? Oops. What's cosine of theta? Well, cosine is opposite. Again, this is tough because this triangle is lying in the xy plane. I don't know, whatever you have to do to squint your eyes or whatever's required to think about it. But cosine is adjacent over hypotenuse. So that's x over the square root of x squared. I don't want to write it like that. Yikes. It's over d. So let's multiply both sides by d, and we get x is equal to d cosine theta. But what was d? D was r cosine phi cosine theta. Now, I've derived this probably over 100 times over the years, and yet, I can never seem to remember it. So there's x. Hopefully you'll do a better job. Hopefully you'll remember it. It'll serve you well. You'll be glad you did. Do as I say, not as I do. Right? Same picture right here. I'm not sure what I can erase right here, but same picture right here. If I have sine of theta, what's the definition of sine? It would be opposite y over d. But d was, well, I just put d right now. So that means y is equal to d times sine theta, but d is this. So r cosine phi sine theta. So there's y. And now z, which I guess I could have done right away. Looking at this right here, let's see, sine of phi is opposite over hypotenuse. And so z, I'm not sure where I should put it. I don't know. Let's put it right here for right now. Z is equal to r sine phi. Okay, so that's the basic introduction to polar coordinates, both in 2 dimensions and 3 dimensions. The basic definitions and the way to go back and forth. You give me polar coordinates, I give you rectangular coordinates. You give me rectangular coordinates, I give you polar coordinates. So it might be nice, this includes me too, since we may be periodically using these, is to write down all these formulas in the boxes so that when we need it, we can refer to it quickly, because I don't want to do this again. Okay, that's enough for this video. More coming up.